So we move to part introduction. Firstly, residential construction. In residential buildings, polymer enhance both functionality and aesthetics. PVC, HDPE, and acrylate are commonly used in plumbing, window frame, roof tin sheet, insulation panel, and decorative element. This material offers homeowner lightweight, weather-resistant, and cost-effective alternative while enabling modern design flexibility. Second is industrial application. Polymer in industrial construction are valued for their strength, chemical resistance, and ease of customization. They are widely used in factories, warehouse, and processing plants for chemical storage, tank, flooring, piping system, and protective coating. The adaptability of polymer allows industrial structure to meet demanding operational requirements, safety, and efficiency. Thirdly, commercial building. In commercial construction, polymer contribute to modern architectural trends and functional solutions. Materials like polycarbonate, acrylic, and epoxy composite are used in facade cladding, skylight, interior partitions, and flooring. Their versatility support innovative design, natural lighting, and sustainable construction practice while reducing maintenance and energy costs. Lastly is infrastructure. Polymer play a critical role in infrastructure projects, including bridge, road, tunnel, and water system. Materials like fiber-reinforced plastic, polymer composite, and PVC are used for pipes coating and structural reinforcement. They are resistant to chemical degradation and environmental wear, make them ideal for long-term durability, reducing maintenance costs, and extending the lifespan of public assets. Okay, what is their importance and real-world applications? First, durable and resistant. Polymer are highly durable material that can resist harsh environmental conditions. Unlike traditional material like wood or metal, they do not easily corrode, rot, or degrade when exposed to water, chemical, or extreme weather. This makes them ideal for long-term use in construction, especially in areas where buildings are exposed to moisture, heavy rainfall, or industrial chemical. Their durability reduces repair and replacement costs, ensuring structure lasts longer. Second is lightweight and cost-effective, easier to build and maintain. One of the biggest advantages of polymer is that they are lightweight compared to material like concrete or steel. This makes transportation, handling, and installation much easier, which can save time and labor during construction. Being lightweight also reduces structural load on foundation. Additionally, their low maintenance requirement and long service life make them cost-effective, benefiting both builder and property owner. Thirdly, versatile use. Polymer are incredibly versatile and can be manufactured in many forms of different construction needs. They are used in pipe and tanks for plumbing and water storage, roof tin sheets for protection against rain, flooring and panel for durability and aesthetic, and window and coating for insulation and weatherproofing. This flexibility allows architect and engineer to use polymer in multiple ways within a single building or across different types of structure. Next is wide application. Polymer have a wide range of application across all sectors of construction. In infrastructure, they are used in bridge, road, and water system, in residential building, for plumbing, window, and roofing, in industrial facility, for chemical tanks, protecting flooring and panel, and in commercial building, for facade, partitions, and skylight. Their adaptability combined with durability and ease of use make polymer a key material in modern construction worldwide. Around 19th centuries, bakelite is a first fully synthetic polymer and invented in 1907 by Leo Hendrik Bakelite. It has a good heat resistant, hard and rigid, resistant to water and many chemicals. For mid-20th century's expansions, from the 1930s onward, polymer production boomed and plastic began replacing or complementing traditional material in many building applications. For example, PVC, polyvinyl chloride, developed in rigid form in early 20th centuries and plasticized by the 1930s. By mid-century, it became a staple in pipes, window frame, and conduits. And for late 20th centuries, advanced composite like fiber reinforcement polymer (FRP) emerged and grew rapidly in civil engineering. This material combines polymer resin with strong fiber for structural reinforcement, retrofitting bridge, building, and infrastructure. Around 19th centuries, bakelite is a first fully synthetic polymer.
Next, I am going to explain about the applications. Polymer materials are widely used in the construction industry, especially for water supply, sewage, and ventilation systems. Common polymers such as PVC, polyethylene, and polypropylene are used because they do not rust or corrode like metals and can resist pressure and chemicals. Therefore, polymers are often used instead of metal pipes. Polymers materials are also lightweight, strong, and low cost. They help with insulation and waterproofing and allow more flexible building designs. Pipes and plumbing systems are one of the most common applications of polymer materials in construction. Materials such as PVC and HDPE, which are widely used for water supply pipes, sewage pipes, and drainage systems. These materials are preferred because they are corrosion resistant, so they do not rust like metal pipes. They are also lightweight, which makes them easy to transport and install, and they have a long service life, which reduces maintenance and replacement cost. Important application of polymer materials in construction is thermal and acoustic insulation. Materials such as polystyrene foam, which includes EPS and XPS, and polyurethane foam are commonly used for wall insulation, roof insulation, and soundproofing panels. These materials help reduce heat loss, which improves energy efficiency in buildings, and they can also reduce noise transmission, making indoor spaces more comfortable. In addition, they are lightweight and easy to shape, which makes them easy to install in different building designs. Another significant application is in flooring and surface coatings. Materials such as epoxy resins, polyurethane coatings, and vinyl flooring are widely used for industrial floors, hospital, car parks, and residential homes. These polymers coating provide strong and wear-resistant surfaces that can withstand heavy use. They are also easy to clean and maintain, and they resist chemicals and stains, making them ideal for areas where hygiene are important. Another important application of polymer materials in construction is in doors, windows, and wall panels. Materials such as UPVC, polycarbonate sheets, and acrylic are widely used for window frames, skylight, and interior and exterior wall panels in residential houses and office buildings. These materials are weather resistant and can withstand exposure to rain, sunlight, and temperature variations. They are also require minimal maintenance and provide good thermal insulation, which helps improve energy efficiency and indoor comfort in modern buildings. This slide shows a case study on the use of UPVC windows in houses and apartments. UPVC is a plastic material that is commonly used for window frames because it is strong and long-lasting. Unlike wood, it does not rot, and unlike metal, it does not rust or corrode. This makes it suitable for outdoor use over a long time. UPVC windows also provide good heat and sound insulation. This helps keep indoor spaces comfortable and reduces noise from outside. Next is the successful implementation and innovation. In energy-efficient houses, UPVC windows help keep heat inside during cold weather and keep heat outside during hot weather. This makes the indoor spaces more comfortable and reduces the need for air conditioning or heating, which lower the electricity bills. UPVC is also used in eco-friendly buildings because it needs less energy to produce than materials like wood or aluminium, then it can be recycled. This helps reduce the environmental impact of buildings and support more sustainable construction. Next is the challenges. Although UPVC frames are strong and they can still deform under certain conditions, long exposure to heat and even temperature changes or poor insulation can cause the frame to bend over time. When structural support is insufficient, this deformation may affect window alignment and overall appearance. And how do they overcome? Weather-related damage can be reduced by selecting UPVC frames that are specially designed to withstand local climate conditions. Using high-quality sealing materials help protect the frame from moisture, heat, and cold. And proper installation and regular inspection also play an important role in maintaining both strength and appearance of the window over time. Next, polymer materials are used in underground water and sewage pipes. HDPE pipes are commonly used for this purpose. They are flexible and do not crack easily, so they can handle soil movement, earthquake, and ground pressure. They also do not corrode like metal pipes, which makes them strong and long-lasting. In the past, HDPE pipes had problems such as leaking joints and poor welding. To solve this, heat fusion welding was developed. This method makes the joints stronger and prevent leaks. HDPE pipes are also environmentally friendly because they are recyclable and do not release harmful chemicals into water. They are lightweight, so they are easier and cheaper to transport and install than metal pipes. As a result, HDPE pipes are now reliable, leak-proof, and widely used around the world for water supply and sewage systems. They can also reduce maintenance costs and increase the lifetime of underground pipes.
Next, we move to the innovation part. First is fiber reinforced plastic. FRP is widely used due to its excellent performance characteristic. It offers high strength, making it suitable for structural applications. FRP is also weatherproof and low maintenance, which reduces long-term repair costs. In addition, it provides a long service life and good anti-slip properties, improving safety and durability. Another key advantage is that it is easily and flexible processed and installed, allowing efficient construction. Next is sustainable polymer contribute significantly to environmental protection. They help reduce carbon emission and resource consumption, supporting sustainable development. This material also enhance thermal control, improving indoor comfort. Furthermore, they address reliance on non-renewable resource, encouraging the use of more sustainable alternatives. Recent innovations have further improved polymer performance. Next is nanotechnology. Nanotechnology refers to the altered the molecular compositions of substances to modify their fundamental characteristics and achieve new properties. Nanofiller like carbon nanotube or graphene derivatives are added to polymer concrete to improve mechanical toughness, increase impact resistance, and provide good conductivity, expanding the range of application. Lastly is smart polymer. Smart polymer offer adaptive features to respond to environmental conditions. They change transparency with temperature, helping regulate indoor lighting. Smart polymer also reduce heat infiltration into building, reduce energy consumption for cooling and air conditioning, improving overall energy efficiency. These sections highlight the advantages, unique properties, and contributions of polymer in the construction industry. First is advantage of polymer. Include being lightweight, which allow easy handling and help reduce structural strain. There are also corrosion-resistant material, enhancing durability. Polymer provide good thermal and electrical insulation, which improve safety and reliability, and increase energy efficiency. Additionally, polymer allows simplified design and cost in construction projects. Next is unique properties. Unique properties of polymer make them highly versatile. They have waterproofing capability, being naturally water resistant and offering good chemical moisture resistant. Polymer are also flexible and impact resistant, able to absorb shock and vibration, increase lifespan and exhibit high toughness. Lastly, example contributions. Example contribution to the construction industry include creating sustainable and eco-friendly structure. Thermal isolation product decrease energy usage, and sustainable construction is supported by recycled polymer. Polymer are also used in pipe and frame made of PVC, coating and paint based on polymer, and insulating foam for roof and walls.
This slide discusses the main limitations of using polymers in constructions. Firstly, polymer materials are more expensive at the beginning when compared to conventional concrete. The cost of producing polymer resins and additives is high, which makes them less suitable for projects with limited budgets. Secondly, polymer needs special installation methods. Skilled workers and specific equipment are required, and normal construction techniques may not work well. If the installation is poorly managed, the quality of the structure may become inconsistent. Finally, there are environmental issues related to polymers. Their production and disposal can negatively affect the environment. Polymers are often considered less eco-friendly because they depend on synthetic materials made from non-renewable resources. This slide explains how these challenges can be reduced. First, attention should be given to the long-term benefits rather than just the initial cost. Polymer materials last longer, need less maintenance, and require fewer repairs. Increasing production levels can also help reduce costs over time. Second, providing proper training is essential. Workers also should receive adequate instruction, and certification systems can help ensure correct application. Working closely with manufacturers can also provide valuable technical guidance on site. Thirdly, environmentally friendly solutions should be promoted. This includes developing bio-based polymers and reusable materials. Recycling systems should be encouraged, and raising awareness of the long-term advantages and increase acceptance of polymer concrete in construction. Next, this slide highlights the future uses of polymers in construction. For structural applications, polymers are used to produce load-bearing components such as beams, panels, and bridge decks. These materials are strong and resistant to environmental damage, which helps structures last longer in harsh conditions. In flooring systems, polymers are commonly applied in industrial and commercial buildings. They can withstand chemicals, heavy loads, and constant wear. These floors are ideal for warehouses, factories, and retail areas, and they can be customized with different finishes and colors. For waterproofing and sealing, polymer materials are widely used on roofs, basements, and foundations. They effectively prevent water from entering structures and help maintain stability in areas prone to heavy rain or flooding. Polymers are expected to play an important role in the future of construction projects. Polymer-based materials help buildings last longer, reduce costs, and support environmentally friendly practices. They also offer flexibility and adaptability, allowing architects to create more innovative and creative designs. As urban development continues to grow, the demand for sustainable and efficient construction materials will increase. Polymer concrete is strong, lightweight, and helps reduce maintenance costs over time. Polymers also provide resistance to chemical, remain stable at high temperature, and offer flexibility in use. The use of recycled and bio-based polymers helps minimize environmental impact. In addition, advanced polymers that can repair themselves and clean their own surfaces are currently being developed. Polymers are also being used in 3D painting, which enables complex and customized construction designs. Furthermore, nanotechnology improves material strength, conductivity, and overall performances. Smart and energy-efficient polymer materials contribute to sustainable development in the construction industry. We have reached the end of the slide, which is conclusion. Polymers show strong resistance to chemical, heat, and environmental damage, which helps extend the lifespan of structures. They reduce maintenance needs and repair costs, making them economically beneficial. These materials are suitable for residential, commercial, and industrial buildings. Polymers resist corrosion, improving safety and durability, and their lightweight yet strong nature reduces structural load, making them ideal for high-rise buildings and bridges. Polymers also provide design flexibility and can be customized to meet specific construction needs. Polymer concrete can include recycled materials, helping support sustainability and lowering carbon emissions compared to traditional materials. In addition, polymers cure quickly, allowing faster construction. They are compatible with modern technologies such as 3D painting and smart building systems. Overall, polymers meet the growing demand for durable, adaptable, and sustainable concrete solutions.